Good morning, students. After the completion of chemical kinetics, electrochemistry, next chapter of physical chemistry is solution. Today, the first class of this chapter, solution, we discuss the introduction, what is a solution, then types of solution. Next, what is a vapor pressure? Then factors affecting vapor pressure, solubility, factors affecting the solubility, then some colligative property. So let us start the chapter solution. So before going to the chapter solution, it is necessary to discuss some few terms are there. Terms are, what do you mean by solution? What is a solvent? What is a solute? What is a binary solution? Ternary solution? What is aqueous solution? Non-aqueous solution? What is a dilute solution? Concentrated solution? So many terms are there. We discuss one by one. First we discuss solution, next solute, next solvent, next binary solution, next aqueous solution, next non-aqueous solution, next dilute solution, next concentrated solution, next unsaturated solution, next saturated solution, next supersaturated solution, next standard solution, next solid solution, next liquid solution, next gaseous solution. These are some common terms used frequently in this chapter. It is necessary to discuss one by one. First one is solution. So what is a solution? It is a homogeneous mixture of two or more components. It is a homogeneous mixture of two or more components present, and its property vary to a certain extent, that is known as a solution. I repeat again, it is a homogeneous mixture of two or more components. If that solution possesses two components, then it is known as binary solution. In that solution, one component present is larger extent, that is known as a solvent, while another component present in lesser extent, that is known as a solute. I repeat again, in a binary solution, only one solute is there. What is the solute? That fraction present in lesser amount, known as a solute, while the fraction present in larger amount, known as solvent. The solution where a solvent is water, known as aqueous solution, while the solution when water not behave as a solvent, known as non-aqueous solution. I repeat again, solution where water behave as a solvent, known as aqueous solution. If water does not behave as a solvent, known as non-aqueous solution. Again, the solution in which the quantity of solute is very low. The solution in which quantity of solute is very low, known as a dilute solution, while the solution is quantity of solute is large, known as concentrated solution. I repeat again, the solution in which quantity of solute is less fraction, known as a dilute solution, while the solution in which quantity of solute is larger extent, known as concentrated solution. Next, the solution in which less fraction of solute dissolve at a particular temperature, then it is known as unsaturated solution, while the solution in which no more quantity of solute dissolve at a room temperature, then that is known as saturated solution, while the solution when more quantity of solute can be dissolved than the required for a saturated solution by increasing temperature, known as supersaturated solution. I repeat again, three terms are there. One is known as unsaturated solution, one is known as saturated solution, one is known as supersaturated solution. First one is unsaturated solution. The solution in which less quantity of solute is dissolved at a particular temperature, known as unsaturated solution, while the solution in which not more quantity of solute can dissolve at a room temperature, then that is known as saturated solution. But the solution in which more quantity of solute can dissolve than required for a saturated solution by increasing the temperature, then it is known as supersaturated solution. Next, standard solution. The solution whose strength is known, whose concentration is known, that is known as standard solution. A solution in which solvent may be solid, liquid or gas. Depending upon nature of the solvent, I repeat again, a solution in which solute and a solvent may be solid, liquid or gas. Depending on nature of the solvent, solution again divided into three types. One is known as a solid solution, one is known as a liquid solution, and one is known as a gaseous solution. A solution in which solvent is solid, known as a solid solution. A solution in which solvent is liquid, known as a liquid solution. A solution in which solvent is gas, known as gaseous solution. So first discuss what is a solid solution. A solution in which solvent is solid, while solute may be solid or liquid or gas, then that type of solution is known as solid solution. Suitable example is amalgam. Next is liquid solution. A solution in which solvent is liquid, while solute may be solid or liquid or gas, then that type of solution is known as liquid solution. Example, mixture of oxygen with water, that is a mixture of ethyl alcohol with water, mixture of glucose with water, suitable example of liquid solution. Next we discuss gaseous solution. A solution in which solvent is a gas. I repeat again, a solution in which solvent is a gas, while solute may be solid or liquid or gas, then that solution is known as gaseous solution. Suitable example, mixture of two gases, oxygen, nitrogen. Suitable example of gaseous solution. These are the introduction terms which are frequently applied in this chapter. Next, we discuss solubility. Next term is solubility. What do you mean by solubility? Solubility of a solute in a solution is defined as solubility of a solute in a solution is defined as the maximum fraction of a solute that can be dissolved in 100 gram of a solution. I repeat again, the solubility of a solute in a solution is defined as the maximum fraction of a solute that can be dissolved in 100 gram of a solvent to form a homogeneous solution at a particular temperature is known as solubility. Next we will discuss solubility of gas in liquid. Next we will discuss solubility of gas in liquid. Almost all gases soluble in water, soluble in liquid, but to a different extent. Suitable example, that is aquatic life. Aquatic life is possible present in a lake, in river, in sea water due to the solubility of oxygen, of the atmosphere, of the air in the water. It is a suitable example which is clear that gases soluble in liquid. Then we discuss what are the factors. What are the factors affecting the solubility? Next we discuss factors affecting the solubility of gas in liquid. There are so many factors are there. 2 to 3 important factors are there which affect the solubility of a gas in liquid. These are point 1, that is nature of gas and solvent. Nature of gas and solvent. That is, next is effect of temperature. Effect of temperature. Next is effect of pressure. We have to discuss one by one. There is 3 important factors are there which affect the solubility of gas in liquid. Point 1 is nature of the gas and the solvent. There are some type of gases, for example, hydrogen, oxygen, nitrogen, dissolve in water to a lesser extent. I repeat again, some gases like hydrogen, oxygen, nitrogen, etc. that dissolve in water to a lesser extent. On the other hand, some other gases like HCl, NH3, CO2 carbon dioxide, ammonia, hydrochloric acid, these are soluble in water to a larger extent, and it is due to the interaction of the gases in the solvent or in the solution. Next is effect of temperature. On increasing the temperature, solubility of a gas in liquid, in water decreases. Important one, remember that. On increasing the temperature, solubility of gas in a liquid decreases. Next, third one, that is effect of pressure. It is an important factor which play an important role for deciding the solubility of gas in liquid or in water, which is given in the form of a law known as Henry law. Let us discuss what is Henry law. Next we discuss, that is Henry law to describe what is the effect of pressure on the solubility of a gas in liquid. That is Henry law. There are two different ways are there. In general, two different ways are there to express this law. The first way, that the amount of solute dissolved in a solvent, the mass of the solute, the mass of the gas dissolved in a solvent is directly proportional to the partial pressure, directly proportional to the pressure of the gas that is present on the surface of the solvent, on the surface of the solution. That is mathematically M directly proportional to P, or M is equal to K into P. I repeat again. The amount of gas, the mass of the gas dissolved in a solvent, dissolved in a liquid is directly proportional to the pressure of the gas applied on the surface of the liquid, on the surface of the solution at a particular temperature. So, M is the amount of gas dissolved in a solvent, P is the pressure, M directly proportional to P. If we remove a proportion sign, is equal to K, K is a proportionality constant. It is one of the form of Henry law. The most important form of the another Henry law, which is usually generally expressed, that is the partial pressure. Mathematical expression is PA is equal to KH into XA. That is the pressure, the vapor pressure of a gas. This is also that the vapor pressure of a gas is directly proportional to its mole fraction. The vapor pressure of a gas is directly proportional to the mole fraction of the gas in the solution. I repeat again. This law says that the vapor pressure of a gas is directly proportional to its mole fraction of the gas in the solution. So mathematically, PA is proportional to XA, or PA is equal to KH into XA, where KH is a proportionally constant known as Henry constant. That means while solving problem, this partial, that is mole fraction of a component given, Henry constant value is given. Question is calculate the vapor pressure of that component. Simply multiplying these two terms, we get the result. Next, discuss what is the characteristic significance of Henry constant. Next, we discuss characteristics of Henry constant, or significance of Henry constant. 2 to 3 points are there. This value of Henry constant depends upon the nature of the gas and also nature of the solvent. Its value depends upon the nature of the gas, and also upon the solvent or solution. Point 2. On increasing temperature, second point is, on increasing temperature, KH value increases. On increasing temperature, Henry constant value increases. That is, on increasing temperature, KH value increases. Third one is, on increasing temperature, that is solubility decreases. Third one is, on increasing temperature, on increasing temperature, solubility of gas in solution decreases. These are the characteristics or significance of Henry law constant. Next we discuss some application of Henry law. Next we discuss application of Henry law. 2 to 3 points are there. Point 1. This law is applicable for preparing, that is, aerated water bottle, for preparing of beverage bottles. That is, when aerated water bottle, that is, gas is given to that solution under pressure. Second one, that is, first one is for the preparation of beverage bottle. Second one, the deep sea diver or the scuba diver, when they move to the deep sea for research purposes, under the deep sea under high pressure, normally oxygen and nitrogen dissolve in the blood, no problem is there. But when the scuba diver came out from the deep sea, then pressure releases, as a result of which the nitrogen that is dissolved in the blood vessel try to escape out. At that time, the scuba diver felt a very, very painful sensation that is known as a bend. So, in order to overcome that painful sensation, the scuba diver used a mixture of helium and oxygen for respiration purposes. The role of helium, not to allow the nitrogen under the high pressure. I repeat again. In order to overcome that painful sensation known as a bend, the scuba diver used mixture of helium and oxygen for respiration. Third one is, at a higher altitude or the hill climber on the top of the hill, the partial pressure of the oxygen is very low. Availability of oxygen is very low. As a result of which, the hill climber or the people living at a high altitude does not require the required amount of oxygen, as a result of which they feel uneasy, not think properly. That is one type of disease that is known as anoxia. I repeat again. The people living at a high altitude or hill climber on the top of the hill, partial pressure of oxygen is low, as a result of which they do not think properly, feel very weak. That felt a type of disease known as anoxia. These are some applications of Henry law. Next term is, that is a vapor pressure. Next we discuss, next term is vapor pressure. What is vapor pressure? The pressure exerted by the vapor. On the surface of liquid at a particular temperature is known as vapor pressure. Then we discuss another term that is known as solid solution. Next is solid solution. What is a solid solution? A solution in which a solvent is solid, known as solid solution. Generally, there are two types of solid solution. One is substitutional solid solution. one is interstitial solid solution. Let us discuss one by one. First is substitutional solid solution. Means one is substituted in one type of solid in crystal lattice. If another one type of solid having similar shape size is substituted, then that type of solid is known as substitutional solid solution. I repeat again. In one type of solid crystal lattice, if that atom or ion or a molecule is substituted by another type of atom, ion or a molecule of the solid having similar shape and size, then that type of solid solution obtained is known as substitutional solid solution. Suitable example, brass. Suitable example is brass, bronze, Monel metal, etc. Second one is interstitial solid solution. That is, in the crystal lattice of a solid, if another one type of solid or atom or ion or molecule that is in small in size are placed in the interstitial position of the crystal lattice, then that type of solid solution is known as interstitial solid solution. In previous case, one type of atom, ion or molecule that is substituted have similar size, but in second case, that one is smaller size, that one is placed in the interstitial position of the crystal lattice of another, then that type of solid solution is known as interstitial solid solution. Suitable example is tungsten carbide. Tungsten carbide is a suitable example of interstitial solid solution. Next we discuss the very important one that is known as Raoult's law. Next we discuss Raoult's law. This law have two components. One is Raoult's law for solution containing volatile component. Another one, Raoult's law for solution containing non-volatile component. So let us discuss one by one. First one is Raoult's law for solution containing volatile component. That is Raoult's law for solution containing volatile component. That is mathematical expression Pa is equal to P naught into XA, Pb is equal to P naught B into Xb. So this law, that is Raoult's law for solution containing volatile component. This law states that the vapor pressure of a component is equal to the product of a mole fraction of its component into the vapor pressure of its component in pure state. I repeat again. This law states that the vapor pressure of one component in a solution is equivalent to the product of mole fraction of that component into vapor pressure of that component in pure form. Let us consider two miscible liquid. Let us consider two miscible liquid A and B having partial pressure of A is PA, that of B is PB, and the mole fraction of that component is XA and XB, where the vapor pressure of component A in pure form is P naught A and that of B in pure form is P naught B. Then mathematical expression of this law is PA is equal to P naught A into XA, PP is equal to P naught B into XB. I repeat again, where A and B are two miscible volatile component, volatile liquid, where P and PP are their partial pressure, X and XB are the mole fraction, P naught A and P naught B are their respective vapor pressure in the pure form. This is known as Raoult's law for solution containing volatile component. Next we discuss Raoult's law for solution containing non-volatile component. Raoult's law for solution containing non-volatile component. This is the important one for exam point of view, for mark point of view. So this law said that the Raoult's law for solution containing non-volatile component, this law said that the vapor pressure of a solvent over a solution, the vapor pressure of a solvent over a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. I repeat again, this law said that the vapor pressure of a solvent over a solution containing non-volatile solute is directly proportional to the mole fraction of solvent. Mathematically, PS proportional to X solvent, where PS is known as the vapor pressure of a solvent over a solution, X solvent is known as the mole fraction of the solvent. Then this law is there, PS proportional to X solvent, or PS is equal to P naught into X solvent. Where P naught is a proportionally constant, is a constant which is known as vapor pressure of a pure solvent. So from this expression, this law may also be stated as, that is, vapor pressure of a solvent over a solution containing non-volatile solute is equal to the product of mole fraction of solvent into vapor pressure of solvent in pure form. I repeat again. From this equation 1, this law may also be stated as the vapor pressure of a solvent over a solution containing non-volatile solute is equal to the product of mole fraction of solvent into vapor pressure of solvent in pure form. So from this equation, one can rewrite that PS by P naught is equal to X solvent, or 1 minus PS by P naught is equal to 1 minus X solvent. Or simplifying, mark that. On simplifying this equation, it becomes P naught minus PS by P naught is equal to X solute, mole fraction of solute. We know it is equation 2. We know for a binary solution, mole fraction of solute plus mole fraction of solvent is equal to 1. So 1 minus mole fraction of solvent is equal to mole fraction of solute. So from this equation, it is clear that P naught minus PS is known as lowering in vapor pressure. And this is total term, that is P naught minus PS by P naught, this is known as relative lowering in vapor pressure. that is RLVP, relative lowering vapor pressure. So from equation 2, this law may also be stated as, that is, the relative lowering in vapor pressure of a solvent over a solution containing non-volatile solute is equal to the mole fraction of the solute. I repeat again. This law may also be stated as the relative lowering vapor pressure of a solution containing non-volatile solute is equal to mole fraction of the solute. If N1 is the number of moles of solvent, N2 is the number of moles of solute, then mole fraction of solute is equal to N2 by N1 plus N2, equation 3. Mark that. We know mole fraction of one component is equal to number of moles of that component divided by total number of moles of the solution. So, putting the value of mole fraction of solute from equation 3 in equation 2, we have that is P naught minus Ps by P naught is equal to N2 by N1 plus N2. This is the mathematical expression. Of Raoult's law for a solution containing non-volatile solute, where P naught minus Ps by P naught is known as RLVP, relative lowering in vapor pressure. N2 is known as number of moles of the solute. N1 is known as number of moles of solvent, and N1 plus N2 is known as number of moles of the solution. Next term is colligative property. Next we discuss colligative property. Next we discuss colligative property. Very, very important term. What is the colligative property? It is a physical property of a solution which depends upon the number of moles of solute, the quantity of solute, the amount of solute present in the solution, but not its chemical nature. That is composition, chemical behavior. Then that is known as colligative property. It is, I repeat again, it is a physical property of a solution which depends upon the quantity of solute, the fraction of solute, the number of moles of solute dissolved in a given amount of solvent in a solution, but not its nature, that is physical nature or chemical nature, how it is made up of composition, reactivity, then it is known as the colligative property. Some examples are there, that is relative lowering in vapor pressure. Next example, elevation in boiling point. Next, depression in freezing point. Next, osmotic pressure. These are some common examples of colligative property. I repeat again. One is relative lowering in vapor pressure. Second one is elevation in boiling point. Third one is depression in freezing point. Last one is osmotic pressure. So let us discuss one by one how to prove that these are the colligative property. First we discuss relative lowering in vapor pressure. First qualitative property is relative lowering in vapor pressure. Already we completed that according to Raoult's law for solution containing non-volatile solute. That is, what is the statement? That is, the vapor pressure of a solvent over a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. That is mathematically PS proportional to X solvent, or PS is equal to P naught into X solvent, where PS is known as vapor pressure of the solvent over a solution, X solvent, that is a mole fraction of the solvent, and P naught is a proportional constant which is known as vapor pressure of the solvent in a pure form. Rearranging this one, we can write PS by P naught is equal to mole fraction of solvent, or 1 minus PS by P naught is equal to 1 minus mole fraction of solvent, or P naught minus PS by P naught is equal to mole fraction of solute. So from this expression it is 2, it is 1. From this expression it is clear that the relative lowering vapor pressure, this is known as lowering vapor pressure, and the total term is known as relative lowering vapor pressure. So from this equation 2 it is clear that the relative lowering in vapor pressure of a solution containing non-volatile solute is equal to the mole fraction of solute. If the number of moles of solute, if N1 is the number of moles of solvent and N2 is equal to number of moles of solute, then mole fraction of solute is equal to N2 by N1 plus N2. Mark that. So putting this value equation 3 in equation 2, we have P naught minus PS by P naught is equal to N2 by N1 plus N2, equation 4. Again, what is N1? That is the number of moles of solvent. What is N2? Number of moles of solute. Again, we know N1 is equal to W1 by M1 and N2 is equal to W2 by M2, where N1, where W1 is known as weight of solvent having molecular mass M1, and W2 is known as weight of solute having molecular mass M2. So putting this value in the equation 4, we have mark that P naught minus PS by P naught is equal to W2 by M2 divided by W1 by M1 plus W2 by M2. We know for a dilute solution, the fraction of solute is neglected, very small in comparison to solvent. So neglecting N2 for a dilute solution, neglecting N2, we have P naught minus PS by P naught is equal to W2 by M2 into M1 by W1, equation 5. So from this expression, our aim to calculate the molecular mass of solute. If relative lowering vapor pressure RLVP is given, weight of the solvent is given, molecular mass of solvent is given, weight of solute is given. If these factors are given, then one is easily able to calculate the molecular mass of solute from this expression. And also mark that from this expression it is clear that RLVP, that is relative lowering in vapor pressure of a solution containing non-volatile solute, depends upon the number of moles of solute. That is the quantity of solute present in the solution but not its nature. Hence, it is clear that relative lowering in vapor pressure is a colligative property.